Hello everybody. Today I would like to talk about the special theory of relativity, Einstein theory. Okay. Okay, the Einstein theory is interesting, but it is kind of hard to believe. Okay, so what about the Newtonian physics before Einstein? Okay, the mass is space and time. The mass of an object, the distance between 2 points, or the length of the object, you can say space, and the time, they are invariant. They are independent of motion. Okay, so according to the Newtonian mechanics. So you can say that space, time, and mass are absolute. This is according to the Newtonian mechanics. But special theory of relativity is something different. So according to the Newtonian mechanics, okay, according to the Newtonian mechanics, the time interval between two events is same for all observers. If you measure the time interval between two events from here, from the surface of the earth, or if you measure from the different frame of reference, you are in the sky, you are in the rocket, and if you measure the time interval between two events from the rocket which is moving, and if you measure from the surface of the earth, it is same according to the Newtonian mechanics. Okay, so the interval of time between Okay, so the interval of time between two events has the same value for all observers, irrespective of their state of motion. If they are at rest or if they are moving, that does not make any change. Absolute. Okay, so but this is according to the Newtonian physics. You can say classical physics also. Okay, and number two, Okay, so another point is the simultaneity is also the absolute. According to classical physics, if two events are simultaneous for one observer and they are simultaneous for all observers irrespective of their state of motion. Okay, so you can say the simultaneity is absolute, but this is in classical mechanics. Okay, and we have one more point. Okay, so the third point is the mass of the body that doesn't depend on the velocity of its motion, independent of motion. Mass is absolute. So these are the points from the classical physics, classical mechanics, Newtonian mechanics. Okay, but in special theory of relativity, we have two postulates. Let me write down the postulates first. Postulates of special theory of relativity. Okay, the first postulate is the laws of physics. The laws of physics are same for all inertial frames of reference. What is inertial frame then? Where you can apply the Newton's law, first law of motion. That is called as the inertial frame. And another frame is we call accelerating frame. Okay. So the first postulate is the laws of physics are the same in all inertial frames of reference. The first postulate. And we have second postulate. The velocity of light is constant. The velocity of light in free space is constant. It is independent of the So the velocity of light is constant. Okay, you know the velocity of light is approximately equal to 3 times 10 to the power 8 meter per second. This is in free space, or you can say vacuum. And this number 3 times 10 to the power 8 meter per second, it is constant. It is independent of the motion of the source, like the source of light, and the observer. If you measure the speed of light in the vacuum, it is independent of your motion. It is independent of the motion of the source of light also. So this is the second postulate. Okay, and we also talk about the simultaneity in classical mechanics, classical physics, the simultaneity is absolute. But here, we can say that the simultaneity is not absolute. Okay, so simultaneity. So simultaneity is not absolute. If two events are simultaneous in one inertial frame, it may not be simultaneous as measured in a different inertial frame. So it is not absolute. Okay. So these are the few points you better to know. And another topic I want to talk is time dilation. Let us suppose this is the rocket and here is the source of light and there is a mirror and light goes here to the mirror and from here it reflects, okay, and there you can have like some kind of detector, something. This is your detector, okay, this is a detector, and let us suppose this distance is whatever you call d, and light goes here up there and come back. I slightly make an angle for this and this ray, like it goes up and return, but it goes up and come down, reflect from the mirror. So actually this is what happened here, but for clarity I just use little angle there. Okay, so how long it takes, it depends. Let us suppose you are here, this is you are the observer. You are the observer and you observe this the ray of light, you measure the time. This is moving with the speed v. So the time you measure we call the proper time here. Okay, let us suppose the time you measure is delta t0. Delta t0 is the time you measure. So you are in the rocket, so you can say that delta t0 is time interval for, you can say, astronaut or space observer, or the observer who is in the rocket. The rocket is moving with speed v. Now what happened is there is another observer here on the earth. If he measures the time, light takes to go from here to there and come back down there. But from the earth, different frame of reference. For the astronaut, the rocket is a frame of reference. For the earth observer, the earth, this, look here, on the surface of the earth, another frame of reference. So what happened? The rocket is moving, so look at this. I'm not going to derive the formula, I directly give you the formula. Okay, so the rocket is moving, let's say from here to there, but what happened is here you have a plane mirror, and the ray of light is also traveling, and light goes like this, here, and from here it reflect, but from this position also rocket moves somewhere there. So it reflect, and look here is the source of light is this, detector is this is the detector, and the detector here, this is the detector, then it goes there this way. This diagram is for you on the the observer who is sitting on the surface of the earth, because light is traveling, the plane is also traveling. Light travel with the speed of light c, the plane travel with the speed v. So light generates from here, but the plane is moving. So this is the path followed by the light for the earth observer. And if, let's say, delta t be the time for the earth observer, okay, time interval for earth observer, okay. So you have a two times, this is delta t0, this is the time for the, like, an astronaut observer who is sitting inside the rocket, okay. For him this rocket is at rest, but for the earth observer the rocket is moving, and the time measured by the earth observer is delta t, okay. And there is a relationship, and the relationship is, please write down the formula. Delta t, this is equal to delta t0, divide this by 1 minus v square divided by c square. This is the formula. This is the formula. Okay, now look at this. If this v is c, then if the object can move with speed of light, here you have to write down c, then c square divided by c square is 1, 1 minus 1, 0, something divided by 0, undefined. Your time is, I don't know, very big. But that is unbelievable. That is very hard to believe. But what happened, what do we know is, so far as of today, nothing can move with the speed of light. I said if v equal to c, if the rocket move with the speed of light, but that is not possible so far. Rocket cannot move with the speed of light. Nothing can move with the speed of light. Okay, so for earth observer, the time interval is bigger, because look, this number, if you plug the speed, the value here, definitely this v is less than c. For example, if your speed of the rocket is, for example, 0.8 times c, if the speed of light is, speed of rocket is 0.8 times the speed of light, then plug here, how much you get? This time is bigger than this time. The earth observer, the time observed by the earth observer is bigger than this, the time observed by the observer in the rocket. This is called as the time dilation. So please write down this formula. Okay, so it is good to know, so that you can solve the very simple numerical problem. Okay, and using this formula, we can also talk about the twin paradox. Let us suppose there are pairs of twins, 20 years old. one point he went to the space using the spaceship rocket, and the rocket is moving with really high speed, and he spent 1 year in the rocket. Then for him, he just spent 1 year in the rocket, right? So now he come back, return, but definitely the Earth observer is not 21 years old only, because the two clock, one clock is in the rocket, another clock is on the surface of the Earth. Those two clocks, they are into different frame of reference. They measure the time from two different frames, so the time looks different there. Okay, so please read the textbook also. Okay, the only formula you need here in time dilation is delta t is equal to delta t0 divided by this. This is the square root 1 minus v square divided by c square. People, they also call this is gamma. You can write down this also. Okay, so this formula, then it becomes delta t0 divided by gamma also. Gamma is square root 1 minus v square divided by c square. Okay, so this is about the time dilation, and there is another one we call length contraction. Length contraction. Let us suppose you are going to one of the planet. Consider you are going to one of the planet. Okay, using the, consider this is the rocket. You are here. You are here, and you left the Earth. So this is Earth, and let us suppose you are traveling to one of the planet. You can call this is like Neptune. For you, the rocket is at rest, but this is coming toward you with a speed v. Okay, and this is Neptune. This planet is coming closer. This planet, this Earth is moving. You passed, moving away. Okay, so this, and the distance between these two planets observed by the observer in the rocket and observed by the observer on the surface of the Earth, they are different. Okay, they are different, and that length, the relationship between the length observed by the observer on the surface of the Earth and the observed by the observer in the rocket is given by this formula. I directly write down the formula here. L equal to L0 times 1 minus v square divided by c square. Now you can see this L equal to so for Earth observer, the distance L0 is the distance for, this is L0 is the distance between this planet and this planet, length or distance for Earth observer. Okay, Earth observer, and for this spacecraft or for this observer who is inside the spacecraft or inside the rocket, L is the length for, you can call, spacecraft observer. Okay, so now you can see that this length and this length, it depends on speed v. If this v is equal to c, for example, if v equal to c, what happens? V square. If v equal to c, then this becomes c square. C square divided by c square is 1. 1 minus 1 is 0. Then you get like a 0. So it shrink then. The length is shrink, decrease. Okay, so this is what we call the length contraction. L equal to L0 times square root 1 minus b squared divided by c squared. This formula we call the length contraction. And if this object is moving, everyone, if this is moving this direction, the length contract in the direction of motion, not this way, only this direction. So what happens is, if this object is moving this way, this shrink like this. In the beginning, at rest, let us suppose this is the length. If it is moving with really high speed, then it shrinks in the direction of motion. Okay, so if you have like this object, consider this is a width, and if this is moving, there is no change in width, only the length. This length decrease, length shrink, the length contract there in the direction of motion. So please keep this in mind. And if you have to solve the problem, you need this length contraction formula. Okay, and so time dilation, length contraction, and we have another one. Einstein, he said that even if the object is at rest, object has a certain mass, even if the object is at rest, that object also has the energy, we call that rest mass energy. Okay, if the mass disappears, then that mass is converted into energy. So he has the relationship between the energy E and mass m. Okay, the relationship is E equal to mc square. This is the formula. So if the mass disappears, then that is converted into the energy. For example, in modern physics, we learn that there is a mass defect. Like in modern physics, somewhere you learn E equal to delta m times c squared. This is called as the binding energy also. But what happens is, for example, if you measure the nucleus of the helium atom, like in helium atom there is 2 proton and 2 neutron. You measure the mass of the helium nucleus, and if you measure the mass of the 2 proton and 2 neutron separately, you do not get the same mass. You have like let's say 1, 2, 3, 4 particles inside the helium nucleus. If you weigh them, this mass, this mass, this mass, and this mass, let us suppose it is 4.5 whatever, let's say 4.4 whatever. Okay, 1 to this mass, this mass, this mass, this mass, and if you combine them together, then 4 particles, it becomes the helium nucleus. Now if you weigh this nucleus at just one time, weigh the nucleus together, you don't get the same mass. This mass plus this mass plus this mass plus this mass, it is supposed to be mass of the helium nucleus, but you get a different. That difference is called as the mass defect. We represent by the delta m. So delta m, and if you multiply by c squared, you get the energy. That energy is binding energy. Now if you want to separate this proton, neutron, if you want to separate them, you have to impart the energy there. How much? This energy. So if the mass disappears, so simply it is converted into energy. So this is the relationship between energy, mass, and speed of light. So this is very the important relationship from the Einstein theory of relativity. Using this concept, we can make a bomb also. Okay, so this is very brief review, very brief review about the special theory of relativity. I don't do the general theory of relativity. The simply special theory of relativity is good enough right here. Okay, so please read the textbook also. Thank you.